Okay.
Hello, hi everyone. I'll just share my screen, then we can start with the session 8 summary, the week 8 summary. Is my screen visible?
Yes, ma'am. Good evening, ma'am.
Yes, ma'am.
Good evening. And is my voice clear?
Yes, ma'am.
Okay. So this week is majorly about continuity and differentiability. But before moving to that, we'll first discuss limits. So in limits, what we do is, let's say you've been graphically, if you try to look at it, let's just say you've been given this function. Let's just discuss it graphically first, and then we'll come to the definition of it. So this is where your x is, right? The values of x. This is the x-axis, this is the y-axis. So let's say this function is f, and let's say this point is a. This is the value of x, right? So if you need to find the limit of this function at x equals to a, what you do is, this is basically written as this, f as x tends to a, right? There are two sides to approach a, right? Approach means if this is a, then to get to this point on the x-axis, you have two directions. One is this one and the other one is this one, right? So this direction is called the positive one. So you write it as if you mean this thing. And what can happen is you can have this thing, right? So in this case, when you will approach this point from the left side, you will get some different limit, which would be this, right? This height would be the limit. And if you'll approach it from the right side, you will get this height as the limit. That can vary, obviously. So we have from both different directions denoted by different signs. So one is this. This is your right one. From the positive direction, it's this one. And this is the negative one, a minus. So if you see something like this means this is your right hand limit. And then your left hand limit is this thing. When you approach a from here, right, from this direction when you come, and this is your left hand limit denoted by this thing. Another important point to keep in mind is when you have a, let's say you have to find the limit of any function. We don't know what the function is yet. You would need something in the neighbor. Neighbor means this thing, right? You would need this thing or something in the domain, right? Otherwise, if this is not in the domain, how would you approach a? Is this point clear?
Yes, ma'am.
So to approach a, approach means, let's say this is a, and this is a plus h1, this is a plus, ideally we do it this way, a plus h1, then a plus h2, and then the closer you get, a plus h3, a plus h4, a plus h5. So you need all these points in the domain because you're going to calculate value at these points, right? So in some, there should be, what we mean here is we need a sequence at least an that tends to a, and this an should be in the domain, right? So if you need to find limit at a, where a is obviously a point, this is clear to everyone, right? A where you find the limit is always a point of uh not necessarily, it doesn't have to be a point of the domain, but it's somewhere there only, right? This thing is in the context of the domain thing, right? And the limit that you find is in the context of your range, right? Is this part clear?
Yes, ma'am.
Okay, you don't have, all I'm trying to say here is if you want to find the limit at a, you at least need one sequence an that tends to a, the same thing that I said here. That comes closer to, let's say you have a1, a2, a3, a4, and so on, so on, so on. So you need this thing to go to a. Otherwise, how will you find limit at a, right? If you can't even come close to a, you can't find limit at a of a function. That's all.
So, ma'am, that means the real value of A1, A2, A3, A4, all of it.
Yeah, you need at least one sequence to be in the domain. That's all. This is your domain. One sequence that tends to A should be in the domain. That's all. And then let's just, do we need to do some examples on limits, or have you already done some on this topic?
Not done it.
Some of them we have done it, ma'am. Some little bit.
Okay. And yes, a very important point that I missed is for your limit to exist, though you must have done it in your last week, but let me just write it here. For your limit to exist at A, let's just say you're trying to find limit at A. Limit at x equals to A. Then your left hand limit should be equal to right hand limit at A, obviously. So this thing, x tending to A plus, should be the same. Sorry, A minus it is. Should be equal to x tending to A minus, A plus. Is that fine? If this is true, then you say that the limit exists. Otherwise, the limit does not exist. And we can do the examples on limits in the continuity topic itself, because in continuity also you need to find limits. So we can do those examples here in continuity.
Ma'am, here we can also say that LHL is equal to RHL is equal to limit at A, na? All three should be equal.
When these two are equal, if these two things are equal, that's the limit then. Obviously, that's when you say that the limit exists and these two quantities, because they're the same, are the limit. So yes, you can say that this is the limit then. If they are equal, then this is the limit. Okay. And coming to the continuity of a function. So in very rough terms, graphically, what you call as continuity is this thing. That when you draw a graph, you don't need to lift the pen. However, we'll see how this thing is not an accurate definition of continuity. Very loosely, we say in graphical terms that when you don't need to lift the pen while drawing the graph, then you say that the function is continuous. But that's not the case all the time. So your basic definition is this thing. The left hand limit at x equals to A should be equal to the right hand limit. So till this part, it was the definition of limits, right? And then you add one more thing to it, which is the value of your function at that point where you're calculating the limit should also be the same to these two limits. And that should be a finite quantity. That's when you say that the limit exists. The function is continuous. So for limit to exist, you need these things. Left hand limit equal to right hand limit. And then that becomes your limit. And for your continuity, you need these three things. At right hand limit at x equals to A should be equal to the function's value at A. So this is for continuity. And this is for limit. Is this fine? We'll see some graphical examples of it then. So let's say you have to find in this one. Now this is a function. It clearly is a continuous function because it's the left hand limit. If you see is this point, right? So graph is it's tending to this thing only. This, then this, then this, then this, and then ultimately this height is tending to this point, right? This thing from the left, and the same goes here. So the height tends to this height that I've marked here from both the sides. And your function's value is also this only, this height only. Is this fine? Does the graphical thing make sense to everyone?
Yes, ma'am.
Yes, ma'am.
Okay. Then this, the same is there, and we have this thing here. So if you look at it, or let's just say I'm not sure if we have this thing here. But this says that it is continuous at x equals to 0. So we'll come to this one later. Let's just discuss the other ones first. Let's come to this one. So the limit, what's the left-hand limit in this one? Let's say this is, yeah, what's the left-hand limit? Let's say this is t. This height is t. What's the left-hand limit in this particular example?
T.
Yeah, t. And what about the right-hand limit?
T plus something.
That upper value.
Yeah, it's if let's say the function is f, then it should be fa, right? If this function is f, then your left-hand limit is because this point is included here, right?
Yes.
So when you have a dot here, this filled dot here, that means this point is included here in this line. And when this is an open dot, this means that it's not included here.
Excluded, yes.
So this means your fa is here, right? So this and this is the limit, isn't it? This point is a comma fa. This is the limit of your function from the right side, right?
Yes.
So it's fa and t, and they're clearly not same. From the graph only, you can see that these 2 points are not same. And coming to this one, now this is your left-hand limit would be this, right-hand limit would be this, and your function's value is entirely different. It's this. So in this case, you're getting all 3 different. Here you got 2 same and 1 was different. And then coming from here, so here your left-hand limit, and so can you see that the limits from both the sides are same? So you're reaching the same point from both the sides. But your function's value is different here. It's filled here. That means your function's value at a is this, right? This height is your function's value at point A. That means your function's value is this, but your limits are this from both sides. That means in this case, the limit exists, but it's not continuous. From which brings us to an important point, which is if you have, I'll write it here. So continuity implies if your function is continuous at A, this implies limit exists, limit of f exists at A, right? By the very definition of continuity.
Yes.
But there's a slight note that you need to keep in mind, which is this only happens, limit of f exists at A only when you have points to approach A. That means, we'll just come to what I meant. Let's just do this example first, and then I'll come to that point. So coming to this particular example, now in this one, the limit is both from both sides. The limit is, what's the limit from both sides?
Infinity.
At A, it's infinity. Because when you come closer to A, your function goes to infinity, right? Your height goes to infinity, keeps increasing, doesn't have a bound, right? And at this point, the value is this, which is not infinity. So if you have, if you have left-hand limit, we don't know what the value is. If you have left-hand limit equals to, let's just forget about this function, left-hand limit, right-hand limit equals to infinity, then can the function be continuous at that point? Let's say at some point C. Your left-hand limit, right-hand limit, both are equal to infinity of some function. We're not talking about any of these functions, of any random function, let's say of G. We have a function G, and the left-hand limit and right-hand limit of G are infinity. And can that function be continuous?
No.
And does anyone want to tell the reason why it can't be continuous?
Because it is discontinuous at A.
No, we're not even discussing A. Let's just say you have a random function, G. We don't know what that function is. And I'm saying that your x tending to C plus, that means your right-hand limit and your left-hand limit, this thing, both are infinity. And can this function be continuous? That's my question. Forget about f and all.
No, ma'am,
About
it
all
cannot
these
be
things.
because there is no definite
And
point
because-
of y.
Because
Okay.
left hand limit will never meet right hand limit.
The reason for this is you would need, yeah. Does anyone else want to add anything?
Ma'am, because there is no definite point of y.
Because in simple words, infinity is not a point on real line. That's the problem. So you can't, even if you were to define such a function, even if you want to make this function continuous forcefully, how can we make this function? Let's say you have, instead of infinity, if you have L here, then to make this function continuous, what can you do? What's the definition of continuity? You want left hand limit, right hand limit equal to the function's value, right? So to make this function continuous at C, what can we do? We can define this function to be L, right? At C, we can define the function to be L. Then it will be continuous at C.
Yes, ma'am. Then it will be continuous if the function's value will be L.
Yeah. So let's say if instead of L, you have infinity here, then I can't define the function to be infinity because infinity is not a real number. That's the problem. It's a limit, right?
Yes, ma'am.
That's not a number. That's why you can't define the function to be infinity at any point. So that's why if you already know that your function is if one of the limits is infinity, then it can never be continuous at that point. Okay. Coming back to
Even for limits, LHL should be equal to RHL is equal to finite quantity.
yeah, the function's value at that point. For the function to be continuous, you'd need the function's value to be the same as the limit.
No, only
That's
for
why-
limits. Should the LHL and RHL be finite quantity, like how we wrote for continuity? And
What?
no, ma'am, should the LH, can you scroll up a little bit?
Yeah.
Here you wrote, no, LHL is equal to RHL is equal to f of a is equal to finite quantity. Like that, this is for continuous function. So for limit
I have
also,
not.
the RHL
I've
should
not.
be
No,
finite
for the limit.
quantity.
See, we have already. It's written here. Anyways, it's written finite quantity here.
Correct.
But
So same
yeah,
like that, limit also should be finite quantity, is it? That was the question. Because you said
it
infinity
should
cannot
be finite, but the limits infinity is also considered to be a defined limit. So if I say limit x tending to a of a function f is infinity, then that's considered the limit of function a. And you don't say that it's not defined.
Okay.
It's the limit is infinity then.
What's the difference between this and the example which we just now said? Here also limit
one?
is infinity only. No?
Yeah, the limit exists here. In this example, the limit exists, it's infinity, but this is not continuous.
Got it. Got it. Thank you.
Okay, and then so what you want is, we've already discussed it. For the function to be continuous, you want the limit, this is your limit, at a to be the same as the function's value, right? And this includes both left hand limit and right hand limit. When you don't put a sign here, plus or minus, that means it's included. Both are included in this one and they are the same, right? So, and we were discussing about the graphical representation of how do we check it graphically. So usually what we do is we see this, that if you don't need to lift the pen, then it's a continuous function. But sometimes what happens, it depends on the domain too. Let's say your domain is 0 to 1, and then you're leaving, and they're taking from 2 to 3. So if this is your domain, union of these two, and then this is your function, let's say. This is 0 to 1, this is 2 to 3. If this is it, and your function is defined in this manner, right? And note that this part is not a part of your domain, right? This is not in the domain. Only this is in the domain. Then this function that we've drawn is considered to be continuous only. Is that all right? So even what happens here is, at this point, at all the other points, let's just talk about point 2. So at 2 point, you can only approach from one side. Which side is it? I can only say, is
Right.
it 2 plus or 2 minus?
2 plus.
Have a look at this graph. Yeah, 2 plus, because you can only approach from the right side, right? You can only approach 2 from the right side because this part is not in the domain. So you can't approach from here. So this cannot be, you can't find the left-hand limit. In this case, left-hand limit you cannot find at 2. Similarly, at 1, you cannot find the right-hand limit. If there's a doubt in this part, I can explain why
Ma'am, but
that's true.
the
And
graph is not
But this is
continuous.
not continuous, right?
this is continuous.
Ma'am, this is not continuous between 1 and 2 now.
That's not how you check continuity. You check continuity at the points of domain. So if you have domain equals 0, 1, union 2, 3, then you're only supposed to check the continuity at these points in the domain. You're not supposed to check continuity at 1.5 because that's not even in the domain.
Okay, if the domain
Yeah,
is
got
there,
it, ma'am.
then it will be not continuous, right?
So, ma'am, you are saying the graph is continuous between 0, 1, union 2 and 3. That's what you're
It's
saying, ma'am?
continuous on its domain. If
Okay,
this
okay,
is F,
fine.
then it's continuous on its domain. And important points are 1 and 2, right? Everywhere else you know why it's continuous. But at 2, there's no left-hand limit, but we still consider it to be continuous. The reason is there's no concept of left-hand limit at 2. Can you see why there's no concept of limit at point 2 in this function? We've already discussed this thing earlier, that if you have A and you need to find the limit at this, then from the positive side, if you want to find the limit, then you want these things, at least something around it, to be in the domain. And there is nothing here that's in the domain, right? You can't, if you're approaching A, let's say this is 2 point, and here you have 1, you can't jump. That means you have to come close to it, right? Very close. So in every interval around 2, there should be a point of domain for you to find limit at 2. And 1 is very far. You can't just jump from 1 to 2. It's like you're approaching a point and you need a path for it, but you don't have a path after 1. So you can't jump from 1 to 2. That's why you can't find the limit, the left-hand limit at 2. Same
So
is
we
the
can
case
say
here.
that for this graph, x is equal to 2 limit exists.
Yeah, the limit, the left-hand limit exists here. Sorry, the right hand. The
Right.
left one's concept is not, you can't even talk about the limit here. So it's, you won't say that
Okay.
left-hand limit at 2 does not exist. You'd say that left-hand limit at 2, you can't find. There's no concept of limit, left-hand limit at 2.
Ma'am, similarly, it goes with 1 also.
Yeah, goes same for 1 from the right side.
So there's no limit at 1 or 2, right? That's what you're trying to say.
Yeah, there's no limit at 1 from the right. So there's no right-hand limit at 1. Left-hand limit is still applicable there.
No, ma'am, if there is only one limit available, right hand or left hand, then it has limit or not?
It's considered to be having a limit then. I just wanted you people to I just wanted this thing to be clear, that it's not always true that if you see something, if there is a gap in your graph, that doesn't mean it's discontinuous. It depends on the domain. That's what I wanted to point out. As in this graph, you see a gap here, right? You need to lift your pen, but this function is still continuous. Same happens there if you
open interval,
What?
right? That continuity is in the open interval 0 to 1 and 2 to 3.
No, it's
Ma'am, how
continuous
can we tell by
everywhere.
looking the graph only?
By just looking, let's say you have this graph, right? This you have this
It's about domain.
till 1 and then 2. And then you know this part is not in the domain. So here you can only find this limit from here. And it should be equal to the function's value at this point. The function's value at this point is this. Limit from here is also the same, right? That means it should be continuous at this point. At the other points, there is no problem. And at these points, you don't find continuity, these points, because they are not in the domain. Continuity
ma'am,
is only to be checked
at
at the points in domain. One sec. Yeah. Yes.
ma'am, so at 1 you are saying that RHR value right hand limit we cannot comment on that, but left hand limit of at 1 we can comment on that. That is
Yeah.
equal to the function at 1.
Yeah.
But if we can't comment on the RHL value, how can we say that by the definition that it is continuous? Because by the definition, if
That's the
LHL is equal
definition of continuity. If there is only one limit, it doesn't mean that the limit does not exist there. Let's not get into the, I just wanted you to have an idea. You don't even have questions like this anywhere. I just wanted you to have an idea that this is also true. Your continuous doesn't always mean this thing where you don't need to lift the pen. It can mean something like this too.
okay, ma'am. Okay.
And the definition of continuity is
In
that
such
only.
cases, we need to know the domain, no?
Yeah. And there's one even more off example for this, which is, let's say you have this function and you define it as this one. This is f1 equals 1, f2 equals 2. So now if you check the continuity, you can't check it at 0.5 because 0.5 is not a natural number. So not going to check the continuity at 0.5. You can check the continuity at 1, and this function, identity function on the set of natural numbers, is a continuous function.
Ma'am, why
It
we
is
cannot
considered
check
to
it
be a
at
continuous
0.5?
function because it's not in the domain. For you to check
Okay.
continuity at, should I write this thing down? To check continuity or to even talk about continuity of function f, you need a in the domain of f. And that's only true for the continuity part, not for the limit part. So if you need to find the limit at a, then a doesn't have to be in the domain of f. But for continuity, because you need to find the value of f at a, no? This is an important point in continuity. It's not there in limit, but it's in continuity. So you need to find the value of the function at a. That's why your function should be defined at that point where you need to find the continuity. Is that all right?
Yes, ma'am.
But for the
Okay.
limit, ma'am, it doesn't mean that it should come in the domain of A. It
No,
can
a
be.
doesn't have to be in the domain of f if you need to find the limit of f at a. Because you don't need to find this, right? You don't need this thing in limit. You just need this thing, fx as x tends to a, right? Is that all right?
So if
Let's
when we are
just move.
ma'am, when we are finding the limit, we can even if A does not come in the domain of the
Yeah, let's
function,
just have an
it's fine.
example. Fx equals to 1 by x. So when you look at this one, and let's take the domain to be r plus. Let's take the domain to be this. So in this case, you have this, right? This is your function. What's the limit at 0?
It does not exist. Infinity.
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 It's infinity.
LHL and RHL.
We don't usually say it does not exist in the case of infinity. We say the limit is infinity. And it does exist because this is not a part of the domain, so you don't have to worry about the left hand. These type of examples are not to be given to you in the exam. This is just for you to understand at this point, this is 0, right? Now your 0 is not in the domain, but you can still find the limit of f at 0. Is that all right?
Yes, ma'am.
For example, take this only. At this point, if we remove this thing, let's say your function is not, in this particular example, your function is defined at a, right? Let's say if it's not defined at a, we remove this point from here. Now this function is not defined at a, but this still has limit, right? Its left hand limit, right hand limit, both are infinity. So it does have limit. And for you to find limit at a, you can still find limit of this function at a, even though your function is not defined at a, right? Same goes in this one. Is that clear?
Yes, ma'am.
Ma'am, if in a function, ma'am, if in a function the limit, if in a function at a value of x, the function is not defined, but the limit can exist at that point,
Yeah,
na?
it can. That's what we've been saying for this long. If this point was not there, let's say at this in this function at a, your function is not defined. That means this point is not in the domain. Let's say your a point is not in the domain. Then you won't see this point here, right? Is this part clear? But your limit still exists, right? You can still find limit. You still have left hand limit, right hand limit equal to this one, this height. But your function is not defined at this point. Is this fine? Can we move on to the next topic if this part's clear?
Yes, ma'am.
Yes, ma'am. Ma'am, there is one point you said in that. You said that in figure 1 and 2, fx is continuous at x. You said we'll discuss that point.
Yeah, this one I'm not sure if this if we have this here, or maybe we just have this here. So that's why I wanted this thing to be clear at this point, because we discussed this. If it's just this thing, if your domain is this, and then this point, is the domain clear to everyone? It's from minus infinity to minus 1, then 1 to infinity, and then 0. If that's your domain, then this function is continuous at 0. That's what we discussed here, because you don't have, your conditions are you need your left hand limit. Let's say this point is 0, right? So your left hand limit at a, right hand limit at a, and your function's value at a to be the same. But in this particular example, there's no concept of left hand limit because you don't have points in the domain. So these points should have been in the domain, but they're not there. This is an isolated point. That means this point, there's one neighborhood around this point in which there are no points from the domain. That's what it means. It's a little complicated. What it means is that if you will draw a neighborhood around this point, you can find one neighborhood around this point, where there are no points of the domain, right? The domain is this. Domain for this is minus infinity to minus 1, union 1 to infinity, and then union 0. And these points, so you can draw a neighborhood. You can have this thing in which other than 0, there are no points in the domain, right? This thing is not in the domain. So we say that this point is all alone, and at such points, if there are any such points in your function, then the function is considered to be continuous at those points. If you see a point all alone and no points around it from the domain, that means that function automatically becomes continuous here. Is that okay? That's what we were discussing here in this example. Where is it? This one. This particular example, where because all of the natural numbers, you have one natural number here, then another natural number here. So there you will find one interval around 1 that contains 1, where there is no point from the domain. That means this point is all alone. It's called an isolated point. At such points, the function is always considered to be a continuous function. Is that okay?
But ma'am, at minus 1 and 1, there is a hole. We can say that. Like there is no defined value of at minus 1, there is no defined value of the function. And even at 1, so how can it be continuous?
But they have only said that it's continuous at 0. They're not talking about minus 1 and 1.
Okay.
Okay. And at this point, because if this is what it looks like, if that means your function is not defined at minus 1, right? And it's not defined at 1 either. That means you can't really talk about continuity at these 2 points. Is this clear to everyone?
Yes, ma'am.
Okay.
You can move forward.
Just keep this in mind that you need the point to be in the domain to check continuity. For limit, you don't need the point in the domain, but for continuity, you need the point in the domain. And if that point is isolated like this, if this is the point and then there is no point, there is one interval around this point, let's say you have 1. And then if you can even find a very small interval around 1, such that there is no point from the domain, that means this point is isolated. And at such points, your function is always continuous. That's the only 2 points we've discussed so far. Then we have this thing. So let's say you have, which are in the domain of function for, so this is the very first point here. So that continuity has to be discussed only at the points in the domain. So the points that are not, we've already discussed this point in detail here. I hope this point is clear to everyone. It just states this only, that you need to have the point in the domain to check the continuity at that point. And then this one is not always true. That's why I was highlighting this thing over and over, that if you see a function and if you see a break there, it doesn't mean that that function is discontinuous. Although it's written here, and although that's how we see continuity. In loose terms, that's how we talk about continuity, but that's not how it's defined. So this is, it's correct.
Ma'am,
Yeah.
what you said, this figure is continuous?
It depends on the domain. If this is your figure, that means your function is not defined at these points, right? So ideally, it's continuous only.
Okay.
Because it's not defined here. But if it's something like this, if you have this thing, then from here, you have this thing. That means at this point, now this doesn't mean that it's not defined here. Your function's defined here. Function's also defined here. The function's defined everywhere and also at the point where you have to check the continuity, but your limits are different. From here, it's different. From here, it's different. Now, this is not the same case as this, right?
Okay, ma'am.
Okay. Then coming to the algebra, just 1 second.
In the
Coming to
last
the
point of
algebra.
that, this one, the last point, the what, equivalently that there are no jumps or breaks in the graph, then for
Okay.
example,
It's the same thing. If you see something like this, let me just make the distinction even more clear. If you see a function like this, where there are no breaks, that means it's definitely continuous. So, in simple words, no breaks implies continuous. But the converse is not true. That means if your function is continuous, this doesn't mean it's not going to have any breaks. This is not true. Is this fine? This says the same thing. Your mod x function is this, right? So it doesn't have any breaks. That's why it's a continuous function. Is this okay?
Ma'am, about the tan x function, it says continuous function in its entire domain.
Yeah.
Oh, while the point is, can you please explain that?
Yeah, what's the domain of tan function? It's
ma'am, the domain is
0
R.
to infinity.
actually, if you talk about the domain, that's we have a defined domain for tan x and every other trigonometric function as well. And your domain is R minus pi by 2 plus n pi. That means so what are these points? Why are we subtracting these points? These are those points where your tan function is not defined at pi by 2, then 3 pi by 2. So your tan function is discuss it here. Your tan function is cos by sine by cos, right? And your cos is 0 at pi by 2, 3 pi by 2, and then all the odd multiples of pi by 2, right? So at all the odd multiples of pi by 2, your tan function is not defined. Or at least it goes to infinity. I don't know the exact direction right now, but it's something like this happens, right? Because your cos x at pi by 2, your cos x goes to 0, and your sin x goes to 1. So this entire thing goes to infinity, right? So your tan as x tends to pi by 2 goes to infinity. But they've subtracted this. So this is not even in the domain. And where do you check continuity? If you have to check the continuity of tan x, where are you going to check? This is your domain. R and all the odd multiples of pi by 2. You can have them as this 2n plus 1 pi by 2. These are the odd multiples of pi by 2. We subtract all these. Where is your function? Where is your tan x? This is where your tan x is defined. So where are you going to check the continuity of tan x?
In the domain.
Domain.
In this domain, right? So your problem is the only points that are going to create problem are odd multiples of pi by 2. But you don't have to check continuity there, right? Because it's not even in the domain. So this function does have tan x is not considered. It is actually continuous everywhere because at points other than this, it's continuous. Is it fine? It looks like this. So tan x curve looks like this, where the only problematic points are these pi by 2, 3 pi by 2. Odd multiples of pi by 2 are the problem, 5 pi by 2. So here it's continuous, right? All these other points, it's continuous. These are the points in the domain. This point is not in the domain. So you don't have to check continuity at this point. This is also not in domain, not in domain. And all the other points, it's continuous. Is that fine?
Yes, ma'am. Thanks, ma'am.
Okay. Now coming to the algebra of limits, this is algebra of limits only. So for the sum, you just directly separate the limit over these two. You can separate limit over this and limit over this. Then provided you have finite limits, what happens is sometimes if you have f's limit as infinity, g's limit as minus infinity, then you can't just separate the limits over f and g. So make sure that your limits are finite. It's not mentioned here, but the limits should be finite. So if your limits are finite, you can use this rule. Same is for the scalar multiple of f. Same is for the subtraction. Same for multiplication and division. In division, you need to make sure of one more thing, that your g should not be 0.
Ma'am,
That
but
okay?
the limits, like it should be finite only. It cannot be infinite. Then the rule doesn't apply here.
Yeah,
Is it so?
because we just discussed, no? If one limit is, say, infinity, and then the other limit is minus infinity. Or actually, even if you separate it, you're going to get infinity minus infinity. Then what are you going to do with it? Infinity minus infinity is one of those indeterminate forms. This is not a limit, right? Just to be clear of everything, just use these rules when you have finite limits. But if you have something like this, let's say the limit of this is 1, and then the limit of this is infinity, right? then you can just say that this entire thing, if you're saying that if this is an, this is bn, this thing goes to 1, this thing goes to infinity, then this entire thing goes to 0, right? Because this is a constant thing and this just keeps increasing as 1 by x. So if your x goes to, if this is the thing, and if your x goes to 0 from the plus side, then where does this thing go? Not
Infinity.
actually take infinity here. If your x goes to infinity, you're taking the wrong thing. If your x goes to infinity, where does your 1 by x go?
0.
0.
It goes to 0, right? So then your numerator is a constant and your denominator keeps increasing. That means it goes to infinity or minus infinity. That means this entire thing, an by bn or f by g, let's say this, f function goes to 1, this function goes to infinity when x goes to a. That means this entire thing goes to 0. Because this keeps, what happens when this keeps increasing? 1 by 2, 1 by 3, 1 by 4. What happens when you keep increasing the denominator and keep the numerator constant? That means this is going to 0 ultimately, right?
Yes, ma'am.
So some forms are going to create, should I just write those forms here? I don't think you're going to see those forms there, but if you see something like this or this, then it's a problem. These forms are the problem. Yeah. These are the forms that you can find. This is 0 into infinity. So if one limit is 0, other is infinity, that's a problem. If you see something like this, or this, then these are the problematic. These are called indeterminate forms. And then you
They're
need to apply
divergent.
L'Hopital's
They're
rule.
not converging.
Yeah, it's not diverging actually, but it's not a, we don't know what this thing is. If you get 0 by 0, you don't know what you get. If you have the infinity into infinity, we know infinity, and when you're multiplying it with infinity, this is infinity only. These are not numbers. When I say infinity into infinity, I mean when one limit is infinity, other limit is infinity, and then you multiply those two functions, the limit is going to be infinity. That's what I meant. But if you have this form, then you don't know what this is. Similarly, if you have infinity plus infinity, this limit is again going to be infinity. We can't really say if this happens. If you have infinity minus infinity, then you can't say what's going to be the limit. Then you use L'Hopital's rule, which we'll come to later. So these are like, it's just simple operation here. Let's just call this operation as multiplication, division. You can use anything here, into, plus, minus, and division, anything. And then if you see this thing, limit, you can just separate them. This is what all of these say, right? And then we have this principle, a sandwich principle. It's called sandwich principle. Let's say you have f here, g here, and you have function h here, and you need to find the limit of these functions at x tending to a. So if you have x tending to a, and you don't know the limit of this function, you can use this rule. If you know that this limit is c, and if you know, let's call it L instead. If you know this limit is L, and this limit is also L, then this limit is also going to be L. That's your sandwich principle. Is that okay?
In the statement, the last line should be limit h of x, right? It's written f of x.
Where?
0.6, the last line, limit x tends to a, f of x is equal to a. That should be h of x is equal to L, right?
Are you talking
No,
about
no,
this thing?
the point number 6.
Rule.
The
Oh, this
screenshot.
one.
Sixth rule.
Yeah, it
This
should
should
be.
be,
Direction.
yeah,
Yeah, it
okay.
should be H. It's H here. So if these two go to L as x goes to A, then this function, which is sandwiched between these two functions, also goes to L. This implies hx extending to A is also L. Let's just do an example on this to make things clear. Let's say you have x sine 1 by x, and you have to find the limit of this as x tends to 0. And what do we know about sine function? We know that it's always between -1 and 1, right? This is application of sandwich principle. So a sine function is always between -1 and 1. That means your x sine 1 by x is going to be between -x and x, right? Or let's just do one thing to make things clear, because what happens is your x can be negative. I'll just come to why I've taken x square instead. Because if you multiply with x, no, what happens is if your x is negative, because we don't know if your x is negative or positive. If you're multiplying x on here, here, and here, then your inequality might change. But that's also not going to matter much. Yeah, it will be the same thing. Let's have x square only. If you have x square here, you just multiply x square on all these three. Multiply x square here, here, and here. So you will get this thing. Sine 1 by x, and then x square. So as x tends to, and you need to find this limit, right? As x tends to 0. So what's the limit of minus x square when x tends to 0?
0.
0. And what's the limit of x square when x tends to 0? It's also 0, right?
0.
So both of these are 0. This implies that your x square sine 1 by x as x tends to 0, this limit should be 0 as well, right? So this means that this limit that you're looking for is 0. That's the application of sandwich principle. Is that okay? But it needs a lot of known things already. Like you should know this thing. And you should be able to come up with this thing in order to do something like this.
So you're saying
Okay.
the range of the full function from where to where, we should know that in order to apply the sandwich principle full.
No, it's sometimes there could be a lot of things. Like let's just say you have fx function, and if you already know that it lies between two functions, h1x and h2x, and if you need to find the function's limit at a, and you already know that this function it's sandwiched between the, so you need to find some functions like this. That is some sort of manipulation that you'll have to do here, right? You'll have to look for, this is something you should know already. It's not going to be that difficult. You won't be given questions like that. But that's how you apply sandwich principle, by knowing that this given function lies between two functions or some sort of those things, which when x tends to a tend to the same point. If you know this thing, then you can apply sandwich, right? Like in this one, we already know that x square sine 1 by x function lies between minus x square and x square, right? If you're able to do things like this, then you can use it, and you won't be needing to use such things. This is something that you should know. Can we move on to the next topic? Let's do some examples then on continuity. So the first, let's take this one. X cos 1 by x when your x is not equals to 0. And when your x is equals to 0, let's take this to dx. So this is your function. And you need to find the limit, the continuity at 0, obviously. Everywhere else it's continuous. You just need to find at 0. So first we find the limit of this thing, right? This is x and cos 1 by x. Now we know, and you should know this thing, that your cos function and sine function always lie between -1 and 1. right? This function and the sine function always lie between 1 and 1, minus 1 and 1. So if you have something like this, that means this thing fluctuates between minus 1 and 1, this thing, right? And this thing goes to 0. As x tends to 0, this thing fluctuates between minus 1 and 1 because that's the value it can take. And your x goes to 0. What should this thing go to then?
0.
This should go to 0. Intuitively, it should go to 0. And if you need a like rigid thing to prove that this goes to 0, you can do the same thing here. Cos 1 by x lies between 1 and minus 1, and then you can just multiply by x on both sides. This goes to 0. This goes to 0. This thing should go to 0. That means this is a continuous function at 0 and at other points too. Other points, so we don't even have a problem. We don't need to check there. And let's do this one, x minus. This is your floor function. Floor function means if you have 1.5 floor function, it
From the
gives you
previous
the
question, we did it with sandwich principle or in general?
you can do it both ways. If you know that something, okay, if you have f and g, and this function goes to infinity, and this function keeps taking some values, some finite values, let's say from minus a to a, or from a to b. So if this function keeps taking value from a to b, and this function goes to infinity, that means this entire thing goes to infinity. Now, if this function keeps fluctuating between a and b, or even if not fluctuating, if it takes values from a to b, and your g function goes to 0, that means this entire thing goes to 0, right? Is that okay? Or should I explain why that happens? It's not needed though. You can just keep this thing in mind.
Okay,
Can we move on to this example? So for your floor function, this value is 1, and for minus 1.5, it should be minus 2, right? This is your floor function. So let's just talk about the continuity of this function then. So let's just start with random points. Let's start with 0. Do you think this function is continuous at 0? Let's check at 0, at x equals to 0. So if you'll take 0, for continuity, what you do is first you find at the value is obviously 0. If this is your f function, then your f at 0 is 0, right? Let's take the left hand limit, the right hand one. So if this is 0, let's take this limit. That means here you will take values that are greater than 0, right? So you do 0 plus h and 0 plus h. And then take the limit h tends to 0. Is this clear why we are doing this thing? It's like you're taking something greater than 0. So if you take something greater than 0, that goes to 0. That's what you do in your right hand limit, right? If I say x
Yes.
goes to 0 plus, that's what you do, right? You take numbers greater than 0 and close to 0. So if you will take something greater than 0, you're going to get the same number here, right? You will get, let's call that number h. You'll get h here. And here, what would you get if you take something greater than 0? You're again going to get h. You're going to get 0 this time, right?
Yes, ma'am.
Is this clear to everyone? Why you're going to get 0 here? Because you will do 0. 0 plus means, okay.
0 point any value.
Yeah, it means this thing,
Less than
0.5
1.
and 0.05. It keeps decreasing and it goes to 0. That means 0 plus. That's what x tending to 0 plus means. That your sequence, there is some sequence that goes to 0 from this side. That means it decreases to reach 0. And then from the negative side, it's this. It's 0.5, minus 0.5, minus 0.05, and minus 0.005. And if it keeps going on, it will go to 0, right?
All those sequence of numbers. Yes, ma'am.
Yeah. So if you have something positive, a positive sequence going to 0, then its floor function should be 0, right? If you'll take the floor of this,
Yes.
floor of this, so it should be 0. So it's 0 here. That means this is h, and h tends to 0, that means this is 0. So limit here is 0, which is equal to the function's value at 0. Let's just check the other limit. This was 0 plus, right? If you need limit h 0 minus, actually you don't need to write it here. We've already taken this into account, right? So if you need to find the limit at x tending to 0 from the negative side, then from negative you will have this. So in place of x, you're going to get x only, right? But in place of this floor function x, what would you get? You have minus 0.5 and minus, it doesn't have to be this sequence necessarily. I just mean a sequence which is very close to 0 and it is
Minus
getting
1.
closer to 0, right? So you can take anything, 0. I've just taken this for simplicity. If this is such sequence, then the greatest integer of this should be minus 1. Greatest integer of this should be minus 1. Of this too, it should be minus 1. That means it's minus 1, right? That means this thing is minus 1.
-1.
So it will be x plus 1, right? And if your x goes to 0, if you put it here, you'll get 1. That means your left hand limit is 1, right hand is 0, and the function's value is 0. That means this function is not continuous, right? At 0. Now, is it just 0 or other integers too? We know that 0, at 0 we have a problem. Let's just try to test it at other points too. So if you have, let's say, any integer, if you have 1 here, the same problem is going to arise because you will do x minus greatest integer x. We'll put x here. From 1 plus, you will have 1 here. And what will you have here?
1.
1. And if you do 1 minus here, you'll get a 1 here. And what about this thing?
-2.
It's going to be, if you'll take 1 minus, that means you're taking something like this. 1 minus, what does 1 minus mean? It means you're approaching 1 from the left side. That means it's a sequence like this. 0
1.00
0.9,
something.
0
0,
0.99, 0
Oh,
0.999.
ma'am, from left. So it should
Yeah,
be
from
1 point
left.
something. Ah, for the digit 1. Okay, sorry.
No, from, if you're approaching it from here,
Yeah,
it
yeah,
should be
sorry.
this,
I was
right?
thinking
It will be
-1.
0.
Okay, that's
Yeah,
all right.
1 is correct. Yeah, 0.
This is going to 1, right? So if you'll take the greatest integer of 0.9, you're going to get 0. Sorry.
0.
If you'll take the floor function, you'll get 0. For this, you will get 0, and for each of these, you will get 0. That means you're going to get a 0 here. So here you get 0, there you get 1. The limit is again not same, and that happens for every integer. It doesn't have a problem particularly at 0 and 1, it has a problem at every integer. Is that all right? So at integers, your x minus greatest integer, this function, is not continuous. And what about non-integers?
It's continuous for non-integers.
Okay, let's just do one random non-integer. Let's say you have a as non-integer, right? And if you'll go a plus of x minus greatest integer x, what would you get here? It will be a, right? And here,
A -1.
yeah, a minus 1. But we don't, yeah, for the, if it's a non-integer, it has to be a minus 1, right? Not minus 1 actually. A minus the non-integer part
A,
there,
sorry. Yeah,
decimal
A.
part. So you're going to get, let's just take a particular number only. If you'll take 1.5, you'll get 1.5 here. And you'll get a 1 here, right?
Yes, 1.
Greatest integer will be 1 from the plus side. when you take 1.5, the keynote here is if you take 1.5 from sequences here, it will be 1.4 49, 1.499, 1.49999, right? The sequence goes to 1.5 from the left side, right? And then let's take another
Yeah.
sequence, 1.5 01, 1.5001, and so on. This goes to 1.5 from the right side. Can everyone see how this is true? These two things. This is a sequence from the left side approaching from here. So you take smaller numbers and then you keep approaching to this point 1.5. And this here you take larger numbers and then you approach to 1.5. So the main thing here is that if you take the greatest integer of these, in both of the cases it's going to be 1, right?
Yes.
It's not going to matter. So in both of those cases, it's going to be that smallest integer only, right? So it's what was happening here is it was changing. In case of integers, the greatest integer, this part was changing, right? Like this changes and this changes. That was creating problem. Same was here. Same was the problem here, right? So greatest integer part because was changing, that was
Because there
causing
was a
trouble.
break at integer. In the
Yeah,
graph, there was a break at integers actually.
because if you will take integers,
Because at the graph, there is a
Those
break in the
function
integer.
changes na at every integer. That is why. Between the
yeah, it
integers
changes
where
at every integer, or it's from here and here, it's okay. I think that's enough. If there's still a doubt in this example, we can discuss that. Otherwise, we can move on to the next thing. At non-integers, this is continuous. This function is continuous. Okay. Then coming to the differentiability part. So this is your definition of differentiability, where if you need to find first thing is to check the differentiability of a function at a given point A, right? So what you do is you take fa plus h here. So if you need to check your differentiability at A point, you do fa plus h minus fa by h, where h tends to 0. What does this actually do? From the and this is for the left hand one. This is for the right hand one, and the other one is for the left hand one, where you take a minus h here. You have all of it here. This is it. So where does this come from? It comes from the definition's clear, right? Then we'll discuss where it comes from. It's basically let's just do it in the derivative. Do we have derivatives? Yeah. This is your, if this thing turns out to be finite, then we say that your function is, if this limit turns out to be finite, then we say that the function is differentiable. Otherwise, we call it to be not differentiable. It's written here. There has to be a finite quantity for the function to be differentiable at A. Either in these two parts, what you can do is either you can just take these as they are given here, or you can just take here. So when you write h tending to 0, this includes both h tending to 0 from the positive side, which is this one, and h tending to 0 from the negative side. Let's just not go there. You can just use this one. That's fine. These things you can just use to find the differentiability of a given function at a point. Let's just do this for one example. Let's just do it here for these ones. And then we'll also, these are some important points that you need to know about differentiability. So if you notice any of these points, The first one is if you see that your function is not continuous at a given point. Let's just say you have to check the differentiability at x equals to a, and you already know differentiability of f at x equals to a, and you already know that the function is not continuous there. That means the function is also not differentiable there. For example, this one, this function, your greatest integer function, it's not continuous at integers, right? At x belonging to integer, set of integers, this is not continuous, right? That means this is also not differentiable. So greatest integer x is not differentiable at x belonging to integers. This brings us to what does this? So this just concludes that if you need your function to be differentiable, you also need it to be continuous. So if a function is not continuous at a point, then it's not going to be differentiable there. Is that okay? So if you see a function which is not continuous at a given point, that means it's also not differentiable there. For example, this one. Then next up we have, let's say you have what does vertical tangent mean? It means this. If you have something like this, like in the case of this, if you have checked the graph of x to the power 1 by 3, it looks like this. And at this point, your tangent is this vertical thing, right? So if you have something like this actually means that your slope is infinity. We'll come to slopes later. And that's why we call it to be not, that means your derivative at this point is going to be infinity. At this point, we consider it to be not differentiable. So if you see a vertical tangent, if you see something like this, and you know that there is a vertical tangent at this point, that means the function is not differentiable there. As in this one. And then if you see sharp corners anywhere in your curve like this, like in the case of mod x, or any function which looks like this, let's say you have this function, and this function is not differentiable here, all of these sharp points, it's not differentiable. Is that okay?
The sharp point has any criteria here? How sharp is it?
What?
The sharpness you are talking about,
Yep.
does it have I mean, even kind of a smoother thing is also kind of considered sharp here, or it's kind of V shape is considered sharp here?
No, anything. If you have, see, sharp, what it means by sharp and smooth. One is considered smooth and the other one's just considered not smooth. So smooth is this thing where you can easily draw a tangent, right? Here at this point you can draw a tangent. But these type of things where you have this thing, a sharp turn, now it's not this thing, right? It's still this thing. Or you have something like this. That's also a sharp turn. So all of these are problematic.
Yeah, my doubt is like the one that you showed the last, the V down. There, if it's instead of being kind of so sharp, if it's even smoother, that is also considered again the sharp, or is kind of smoother. It will be considered smooth there.
Are you talking about this
If
one?
it's not too sharp, the edge when it's kind of smoother compared to
If
the
you've been
current.
asked to identify a graph and you have to identify if a function is differentiable or not just by looking at the graph, then you will be given clear signals. Won't be given something which you can't tell if it's smooth or if it's not. If it will be given, it will be given like this. You can clearly see that there is a sharp turn.
Okay.
You won't be given something like which looks like you can't identify if it's smooth or not. That won't be given.
Yeah. Okay. Okay. Thank you. And in the case of the differentiable and the continuous thing that you mentioned in the discussion, so it is also not integer there when it is
Here?
differentiable and not continuous. So
Yeah,
so
if a
it means
function
in
is not,
integer.
yeah, at integers it's not differentiable because it's not continuous there. So any function which is not continuous at point A, then that function is also not differentiable at that point.
Oh.
We have that as a separate point here, I guess. Here. We have it here. So if you have a differentiable function, that means your function is continuous. And this is the contrapositive part of it. So if your function is differentiable, this implies it's continuous. Or in other words, you can say if your function is not continuous, it's the same thing, right? These two are basically the same things. Not continuous implies not differentiable. Same things said in different manner. These two are true. They're written here, but the converse is not true. If your function is, say, continuous, you can't tell if it's differentiable or not. Then you'll have to check. Same goes here. If your function is not differentiable, it can still be continuous. This converse is not true. Here also converse is not true. It can be in some particular examples, but in general, it's not true. And then you have some functions given here that are obviously continuous. Your polynomial functions, rational functions are these ones. P by Q functions, where your Q is not 0. And these are called the rational functions, where both of these are. It's basically the algebra of functions only, right? Where both of these functions are continuous. So obviously the quotient is also continuous. Then your trigonometric functions are continuous. Logarithmic function is also continuous. And exponential functions are also continuous.
Ma'am, what was the point you said in Px upon Qx?
I was just defining what a rational function is. So rational function is Px by Qx, where these are the rational functions actually. Rational functions are ratio of two functions. But for rational functions to be continuous, you need to make sure that both the quotient with the numerator and the denominator are continuous, right? Is that okay? You need to, this is the same as this part, that if your Px is continuous, your Qx is continuous, that means your Px by Qx is also continuous. Same thing. And in general, okay, we'll discuss that later. Is it clear till this part?
But do we have any exemption to this rule?
This rule?
Huh.
No, I don't think so. We don't have any exemptions, no exceptions to this rule.
Okay.
So if you have a differentiable function, then it's always continuous.
Okay.
Coming to this one, derivative, it's denoted by this. Either you denote it by dfx by dx, or you denote it by f dash x. Same thing. And it's basically the same limit that we were trying to find when we were discussing differentiability, right? This is the same limit.
Ma'am, this fx plus h minus fx, this is the right hand derivative, na?
Yeah, the right hand one.
And x minus fx
Here
minus
you,
x minus h is left hand derivative.
thing is, here you have both included. It's 0 plus and 0 minus, both included. So if you're trying to find the limit, it's like limit at 0. So if you take limit from 0 plus, that's your your right hand derivative. From 0 minus, it's left hand derivative. So it's both included.
It's for a
In this one, it's
continuous
both
function,
included.
right? So you don't need left and right hand since it is continuous.
What was the point you said last? Fahad, whoever it was.
You'll get this derivative if it is continuous, right? You'll go to this step
No,
if it is continuous.
this function we're talking about.
Yeah,
This is
but
the
it has to be
function.
continuous to find derivative, right? Then you don't need to do left hand and right hand.
But f has to be continuous. No, fx plus h minus fx is this is a different function. This is a different function. If your f is continuous, it doesn't mean this is also continuous and the limit is going to exist. If your f is a continuous function, then the limit of f is going to exist. This is a different function. This might not exist. Is that okay?
And what was the last point you said?
Someone just mentioned that if you are doing this thing, you don't need left and right hand because you know that the limit already exists. That's not true. The limit f is continuous, that implies the limit of f exists at whatever point it's continuous. It doesn't mean that this limit also exists. That's the only point. When you look at it here, yeah, so you have a plus h here. If instead I'll just do, here you have h tending to 0, and you have been given that your h is greater than 0. What does this mean? That your h, it means this thing, right? When you say your h is strictly greater than 0, here you have mentioned that your h is strictly greater than 0. That means this thing that you're doing for the right hand derivative is this. And for the left hand, it's this. 0 minus, you can do it as this. fa plus h minus fa h. Now, when you do this thing, it automatically means you're taking negative things, right? So if you have to write it in positive manner, you will write it as this. H tending to 0, fa minus h minus fa by minus h, which is the same thing here, right? Is that okay?
That's you're saying the writing style. We can write it in any way, na?
Yeah,
That
you can, but just make sure that the easier way to do is, that's how I remember it. And this is the limit, and you take the limit from both sides, right? You need this limit to exist. Take the limit from the positive side, that's your right hand derivative. Then take it from the negative side, that's your left hand derivative. Then you don't have to remember this thing. This minus h plus h. Is that okay? Is there a confusion in this? If there's any doubt in this thing, I can just repeat this entire thing.
Ma'am, this is fine. What you told us that that we don't have to write both of them because we can sum it up in one way where we can say that h
This
tends
is summed up in one way, but
yeah.
you'll have to find both of them. You'll have to find the left hand derivative and the right hand derivative both to make sure that they both are equal. That's when you say that the limit exists, right? Forget about the derivative thing. Just look at this function. You need the left, for this limit to exist, you need both left hand limit and right hand limit, right?
Yes,
The
ma'am.
left hand limit of this entire function is the left hand derivative of f. And the right hand limit of this entire thing is the right hand limit of f, right hand derivative of f. Is that fine?
Ma'am, can we do an example of that?
Yeah, we can do an example on that. Let's just do this one. Is it okay if I take mod x1? Let's do mod x. Now you have two derivatives, right? One is left hand derivative. For that, what you do is f, and at 0 you're trying. At 0. Derivative at 0. So you'll do f0 plus h minus f of 0 by h. This time you take h tending to 0 plus from the positive side. So from positive side, if you do, this is mod h minus f of 0 is 0, and then you have an h here, right? H tending to 0 plus. So this thing is going to be h by h. It's going to be 1. Why is it h? Because it's 0 plus. That means you're taking numbers greater than 0. 0 0.5, 0 0.55, sorry, 0 0.05, 0 0.005. So you're taking numbers positive. That means the mod, this thing, mod is going to be positive, right? So I can just write h here. I know that it's going to be h because you're taking positive numbers here, because you're approaching from the positive side of 0. So it's going to be h by h, which is 1. Now for the right hand derivative thing, you do h tending to 0 minus, same thing. So it's this h minus 0 by h. Now if h tends to, this is minus h, right? And this is h. And this is going to be minus 1. So both the derivatives are different. The left-hand derivative does not match with the right-hand one. Important part is, how do you know this mod h is equal to minus h? Because it's negative this time. We'll take minus 0.5, minus 0.05. So the mod of this is going to be minus of minus 0.5, which is 0.5, right? Is that clear why we've taken a negative sign here? Because
Yes,
the
ma'am.
values of h are negative. That's why we've taken a negative h. Here they were positive. That's why we've taken a positive h. Each time you get a different derivative, that means this function is not differentiable.
Ma'am, when we took h function 0 plus h minus that in the last one,
Yeah. This one,
when we were taking the example just previous one, when we took LSD, left hand derivative, we took 0 plus h minus function of 0. Yes, ma'am.
this is your right hand one.
Yeah, ma'am. It's the right hand derivative, I was thinking.
Thanks. This is the left hand one. This is the right hand one.
For the left hand derivative, isn't it 0 minus
It's 0
this,
minus only.
like,
This is 0 minus.
no, in the numerator it shouldn't be like 0 minus h. Like, I know the writing style is like that. When we solve it, the left hand derivative, we write it like that only. But in general, it should be like 0 minus mod of h, na? Graphically speaking.
Yeah, and
Well,
even
this one,
bit bottom it will be minus h then, so it's the same.
Like,
If you
graphically
use
speaking,
other formula, it will be 0 minus h minus f of 0 upon minus h. If you're taking it 0, you get the same answer.
if you take this thing greater than 0, that's what I was telling there. If you take this, that's your doubt. If you take this to be positive, where they're taking here they take it to be positive. In both the cases, what we are doing is, in one case, we are taking positive. In the other one, the left hand one, we're taking it to be negative, right? We're
yes,
taking
ma'am, but
h to be
for the
negative.
left hand derivative, it should be fa minus h minus fa. So I know in most of the example,
It's the
it is
same
like,
thing. You will get the
Yeah, but
same
if you see
thing.
the denominator is minus h over here, right? So you'll get the same answer.
okay.
That's the difference. Here you have minus h, there you have h only. You're doing nothing here. What you're doing here is, in this one, in this particular example, because you're going to change it, right? H greater than 0. And for the left hand one, we are taking h less than 0. The way we were doing it, we took h less than 0. So for this, you change the sign here. So the sign of minus h gets changed, sign of minus h gets changed. So you
So
are left with this thing only. So if, in simple words, if you're taking h less than 0 for left hand derivative, use this. If you're taking h greater than 0, use this. Same thing, no? What's the difference?
yes, ma'am, because the denominator, the sign of
Yeah.
denominator minus, we transfer it to the numerator. In a way, we are saying that, na?
Yeah, we're just replacing minus h with h here. Is that okay? Okay. Let's move to what were we doing? Last thing that we were doing was this, right? Yeah. So this is called your derivative. When your left hand derivative, right hand derivative match, then that's called your derivative, and it should be finite, right? And what does it represent actually? It's your instantaneous change. Instantaneous rate of change of y with respect to per unit change in x. So it's like this thing. Here I'll just do this. What's your how do you find the rate of change in y with respect to per unit rate of change in x? At point A. Let's say you have to find the change at A. So how do you find the rate of change of f at A per unit change in x? Isn't it the same thing as this? Right?
Yes, sir.
That's how you find the per unit change, right? This is the change in y at a, and this is, if you divide it with the change in x, you'll get change in y at a per unit change in x, right?
Yes.
So this is your change in y per unit change in x. And for instantaneous, you do this thing, limit h tending to 0. Instantaneous means you want the time interval, this interval, to be very small. So this interval you want very small. For that, you do limit h tending to 0. Okay. Then we have the rules for differentiability. The first is your sum rule, where if you have to find the derivative of this thing, you just simply find the derivative separately. Let's just take one example. Let's say you have x square plus x. Or let's take simpler examples. Well, let's take x plus x square only. So the derivative of x is 1. Just 1 second. Yeah, so uh, your sum rule is, first you find the, so instead of finding the derivative of this entire thing, first you find the derivative of the first function. This is your function, and then this one. So if it's in sum, you can just directly find the derivative of this. What the derivative of x is 1. We'll discuss, I'll just give you all the derivatives, the important ones, at the end of this session. So the derivative of this is 1, and the derivative of this thing is 2x. The derivative of this entire thing is going to be the derivative of this plus the derivative of this. And then you do the same for subtraction. It works for subtraction too. For product, there is a different rule. So here what you do is, first you take the derivative of f and you keep g constant, and then you take the derivative of g and keep f constant. Like if you were to take x sine x, again for that you need to know the derivatives of x. But now just remember that the derivative of x is 1 and the derivative of sine x is cos x. So the derivative of this entire thing is going to be, first you take the derivative of x, which is 1, and keep sine x as constant. And then you take the derivative of sine x, which is cos x, and keep x as constant. So this is going to be the derivative, which is x cos x plus sine x. Is that fine? Let's say if you have sine x by x, and to find the derivative of this thing, you can't obviously talk about this function at x equals to 0. So let's say we've defined this function for x not equals to 0. So here, if you'll apply the quotient rule, your quotient rule says, first you take the derivative of this function, you keep the other one constant, the denominator constant. Now there has to be an order here. Derivative of this first and keep this one as constant, because there's a negative sign. There we had positive sign, so it didn't matter what you take first. And then you take g and the derivative of divided by the square of the denominator. This is the rule. So if we'll apply it here, what are we going to get? So for your f is sine x here, so we'll get cos x. And for g, you'll keep x as constant. And you'll take, okay, we've written the same thing here. G dash f. So you'll take the derivative of
Cos,
g then,
cos
which
x
is
upon
1.
x.
Okay, let's see. Let's do it step by step. Only one example. So, and then f is sine x, right? So it's this thing divided by the square of x. This is going to be x cos x minus sine x by x square. The general derivative we're talking about. Is this fine? Discussed all rules here. And then we have one more rule, which is your chain rule. Which is this. If you have f x composed with g and you're taking the derivative of this entire thing, then it's equal to the derivative of g and your argument should be fx. And then take the derivative of f. Let's say if you have composed sine with cos, and let's say you have composed sine with x square plus 1. Then the derivative of this thing should be, first you take the derivative of this outer one. So you'll get cos and keep this argument same. So keep the argument as fx. Your fx is x squared plus 1 here, right? This is your fx and sine is your gx here. So keep this thing as same and then take the derivative of fx. So it will be into 2x. So it's going to be 2x cos x squared plus 1. Is this thing fine? Is this clear to everyone? Okay. Then coming to your indeterminate limits, which is you will generally be seeing these forms only 0 by 0 or infinite, and at most it could be 0 into infinity. That's it. Mostly will see these two forms only 0 by 0 and infinity by infinity form. So if you ever try to solve this thing and you see that the limit of this thing fx is 0, limit of gx is also 0, or you see that the limit of both of these is infinity, so getting infinity by infinity form, then is when you can apply the L'Hopital's rule. So what does your L'Hopital rule says? It says that if you have f by g and the limit as x tends to a of both of these is an indeterminate form, either this one or this one, then what you can do is you can, instead of finding the limit of this, it's actually the same thing. You can find the limit of these two things. So before moving on to the L'Hopital's rule, let me just write down the basic derivatives that we have that you need to know.
Ma'am,
So
can
that
we
we can
distribute
just,
the limits that you have written, like limit x approaching to fx by gx? Is that equal to limit x approaching to a fx by limit x approaching to a gx?
so you can't separate. See, if you will separate the limits here, no, if you get 0 by 0 form, that's a problem, right? If you write this thing as limit f by limit g, and then you get a 0 by 0 form, and that's a problem. What you do next is you do an example on this. Instead of finding the limit of both of these, you find the limit of limit extending to a dash x by g dash x. Then you separate limit over these two. Now, if you're still getting 0 by 0 form, it's double derivative. F dash double x by g dash double x. And then solve it and find the limit. Each time
Yes,
you get a
ma'am.
0 by 0 or infinity by infinity form, move on to the next derivative. But sometimes
Yeah.
it's you can't solve it using this thing. You're not going to get examples like that in exam.
Yes, ma'am. Like in this practice assignment, one was there. Like this type of question was there. Like L'Hopital rule we are able to apply, but this option was there. Like limit x approaching to it, they were distributing that. Like is that true or false? And they said that the statement is false. That thing.
Which question is it?
It was in practice assignment, practice assignment non-graded one. That week 8.
Which question is it?
That was one multiple correct one. Let me check once, ma'am. Just a second.
We can discuss it towards the end of the session. Is that okay?
Okay, ma'am. Yes, ma'am.
Okay.
Yes, ma'am. No problem. Thank you.
So, for example, this one, let's just say you have sine x by x. So we know if you will take the limit here, limit sine x by x, you can't do, this is not how you do it. The problem is, if you do this thing, you'll get 0 by 0. That means you can't apply this rule here, right? The separating limits over the numerator and denominator, you can't do here. Because you're getting 0 by 0 form. So if that's the question, you can't separate the limits over these two if you're getting an indeterminate form. Where you get this thing, that means what you should be doing is you should take the derivative of sine x, which is cos x. Then take the derivative of x, which is 1. Should I just write down the derivatives first? I'll just write down
Yes,
the
ma'am.
functions and their derivatives first. Function and the function's derivative. So if let's start with this one. If you have x to the power n, then this is n x to the power n minus 1. The derivative of this is n, you take here, and then x to the power n minus 1. The second one is sine ax. So the derivative of sine ax is a sine ax. You can apply that rule, the composition rule for derivatives, where you find, sorry, this should be cos. Where you first find the derivative of sine, which is cos, keep the argument same, ax, and then find the derivative of this argument, which is a. And third is cos ax. Same way, you can do this will be a sine ax, but the derivative of cos is minus sine, so it's this. Then you have e to the power ax. The derivative of e to the power ax is a e to the power ax. And let's say you have e a to the power x, where your t is a number, right? T is a real number, let's say. And this thing should be a t to the power ax, but you'll have to add this thing, natural log of t. And then for log functions, for natural log, it's this. If you have natural log of x, your derivative is 1 by x. But if you have log base ax, then it's 1 by x and then natural log of a here. So these are the derivatives that you should know. Now let's just come to this one. So sin x derivative is cos x, x's derivative is 1, right? From here, from these formulas only. And then you apply this limit extending to 0. So cos x is limit. Now you can separate these two limits because these both of these are finite. Extending to 0, cos x, and extending to 0, 1. Both of these limits are finite, right? In other words, you're not going to get 0 by 0 or infinity by infinity form here. So you can separate the limits over these two. So this is going to be extends to 0. So this is 1, right? This limit is going to be 1. Similarly, you can do it for this one. If you first just test if this is a 0 by 0 or this is a very important point here is this is only true when this limit is of the form 0 by 0 or infinity by infinity or infinity. This is only true in these cases. If you don't have these cases, then you can't apply L'Hopital's rule. Then this limit and this limit can be different. So first check if this is a 0 by 0 or infinity by infinity form or not. So if you'll put 0 here, you'll get 1 minus 1. We're doing it quickly. And if you'll do a 0 here, you'll get this. That means this is 0 by 0, 0 by 0 form. So you can do the same here. Should we do this one or can you guys try this on your own?
We can use L'Hopital rule in that, no?
That's what these examples are for. Both of these examples are for L'Hopital's rule only. Use L'Hopital's rule because it's 0 by 0 form. Take the derivative of both of these. and then you will be done. And by the way, you'll have to apply the L'Hopital's rule twice here because it's 1 minus cos x and x squared. So if you take the derivative one time, you're going to get sin x by 2x, right? And then if you'll take x going to 0, this is again 0 by 0 form. So you will have to apply L'Hopital rule one more time on this. This will be cos x by 2 as x tends to 0. Then you'll get half. Is that okay?
Yes.
Maybe we can do one more example on L'Hopital's rule, this one. Let's take this one. First, just tell me if I should be applying L'Hopital's rule here or not. Do we need to apply, can we apply L'Hopital's rule? There's a condition to apply L'Hopital's rule, right? You need 0 by 0 form or infinity by infinity form. That's what you're going to get in these forms, or 0 into infinity form.
Yes, ma'am, we can apply because it's 0 by 0. 1 minus
0
1
by
upon
0 form. Let's try to apply it then. If you'll do this thing, what's the derivative of e? This is a composition of two functions, right? E and sin x. So for the derivative, first you take the derivative of e to the power fx, which is e to the power sin x. It's going to be e to the power sin x only. And then you take the derivative of sin x, right? So it's going to be cos x.
Formula. Like it will have a sin x minus 1 by sin x into sin x, that will be whole thing 1. So sin x by tan x we have to solve. That is sin x by cos x. So cos x, and when x is 0, it will be 1, 1 will be the answer.
What? Are you suggesting any other method for this?
Yes, ma'am. I was saying that we don't have to use L'Hopital here, I think. Like we have one formula, no? It will have a sin x minus 1 divided by sin x into sin x.
Yeah, you
So,
can do that. But
yes.
you can apply L'Hopital's too. If someone can come up with this thing, sin x and tan x. So this is sin x into cos x.
Yes. So cos 0, 1 will
This
be
gets
there.
cancelled, and this will go to, I think this goes to 1.
1.
E to
Yes,
the,
1.
yeah, this goes to 1, and this is going to
1.
so this is also going to 1. This
So
entire thing
1.
is going to 1. That's also fine. You can do it using this method, or you can use L'Hopital's rule,
Yes,
which
ma'am.
will give you e to the power sin x cos x, and then here you'll have the derivative of tan x is secant square x. You can check the derivatives of all trigonometric functions on Google. So here you'll have, and your secant square is nothing but 1 by cos square, right? Your cos is 1 by secant x, right? This thing is going to be e to the power sin x cos cube x as x tends to 0. So this thing is going to 1. This thing is going to 1. So it's the same thing, 1. You can do it either way.
Ma'am, and there is one student who said that e to the power sin x minus 1 upon sin x, is it 1 by identity? This one?
Yeah, it's e to the power sin x minus 1 by e by sin x, right? So what?
So is it 1?
Yeah, it's 1 because when your x tends to 0, sin x also tends to 0, right?
So
This
it's
is
an
1 because
identity.
sin x tends. It's not an identity. What happens here is if you have e to the power fx minus 1 by fx, and you know x tends to 0, you find this, you need to find this limit. Then what you do is, if you know that as your x tends to 0, fx also tends to 0, like x tends to 0, that means sin x also tends to 0, right? So your x, when your x tends to 0, if your fx also tends to 0, then this limit is going to be 1 only. Because you can replace that fx by, let's say, y. So you can do e to the power y minus 1 by y as your y tends to 0, right?
This is an
Y
identity,
is this
ma'am.
thing.
E
It
to the
happens
power y.
everywhere. Even if you have sin fx by fx, that's an identity. E to the power x minus, yeah, this is an identity. And this
That's
is the
what
result.
I was talking about.
Yeah. This is the consequence of that identity. Okay. Same goes for these also. Sin fx by, if you see something like this, sin fx by fx, or 1 minus cos fx by fx. Okay. Coming to the equation of, let's just first discuss what tangents are. So if this is your graph, tangent is basically a straight line that passes. If you need to find your tangent at a, at x equals to a, say this is your x equals to a, so your tangent would be a straight line that passes through this point a comma fa, passes through, it just touches this point and then leaves. So it touches this graph only at a comma fa. That line is called a tangent at a, right? So this is tangent to f at a. Now your tangent is a straight line, right? And what's the slope of straight lines? So slope of straight lines is constant, right? Constant means it's a constant number, arbitrary constant. Just one sec. So if this is a tangent to your curve at the point A, then the slope of the straight line, this is a tangent is always a straight line, and the slope of a straight line is a constant term, right? A constant, like the straight lines are of this form, right? Mx plus c. So the derivative of this is slope of, by the way, the slope is the derivative only. Let me just write that down first. So derivative of f is the same as, it gives the slope of f. For example, if you have x square plus 2, then its derivative is 2x, right? If you need to find the slope of x square plus 2 at 2, slope of x square plus 2 at 2, then it's going to be f dash 2. Your f dash is 2x, that means it's going to be 2 times 2, so it's 4. So for a straight line, it should be the slope of the straight line is going to be m. If your straight line is of this form, y is equals to mx plus c, then your slope should be m, right? So it's a constant thing. So of a straight line, the slope is constant. So the slope of this line is constant, and the slope of this function at point A, your slope keeps varying at every point. At this point, your slope is something else. At this point, it's something else, right? And the slope at any point is the same as the slope of the tangent at that point. So the slope of this function, this entire curve, f at this point A, is the same as this tangent line. And the slope of this function at this point, let's call it C, is the same as the tangent at this point. The slope of both this tangent and this curve at C is same. Is this point clear?
Can you just take a right? I'll take a screenshot of that.
If you can reiterate that, ma'am. Thank you.
Thank you, ma'am.
Hello.
Yeah.
If you can reiterate that. I lost you due to computer internet connectivity. I lost you for
Okay.
last minutes.
I'll just repeat this thing. The only thing that I've discussed here is your slope of tangent to f at A point is the same as slope of f at A. So that means the slope of this line, this tangent line, is the same as the slope of this curve at point A. For this curve, the slope keeps varying, but for the straight line, the slope is constant. I hope you know that the slope of a straight line is a constant number. We've discussed it here by
Yes.
but that's true. Okay. When you try to find the equation of this, let's just say you need to find the equation of this line. How do you find the equation of a straight line?
Y is equal to mx
Y
plus c.
minus y1.
Yeah.
Y minus y1. And do we know a point on this? What point should we be taking?
Ma'am, we will be taking that.
Tangent.
Yes. Y minus f of
Y
a
and x intercepts.
Yeah, y minus fa.
equal to
Because this
m
is the
minus.
point that lies both on the curve and the straight line, right? So for
Yes,
the
ma'am.
tangent, you should be taking this point, y minus fa, x minus a, and then the slope,
M
right?
times m.
This is it. But this is the slope. You can call it both ways. Either you can say that this is the slope of the straight line, and it's the same as the slope of this curve at the point A. Both are the same things, right? So this is the equation of tangent. Let's just okay. Then next up, we have linear approximations, which uses the concept of the equation of tangent. It's the same thing, by the way. So, and I will also come to what's the difference between linear approximation and the tangent. So linear approximation basically means if you have this curve, let's say you have this curve. So what happens is if it's a tricky curve and you don't know what the values are, right? Like let's say you have e and you have to find e to the power 0.01. And if you need to find this value, you can't, right? Just by hand, you can't find the value of this. You'll need something, right? Some tool to find the value. So what we do is if we have a graph of this sort, we try to approximate this thing. So instead of, and how do we approximate it? Let's say this is a point A. So if you need to find the value of this curve at a point very close to A, let's say you have this point which is very close to A. Very close means if this point is 1, then this point is 1.005. This is a close point to it. Then what you do is instead of finding the value of this, so instead of finding this height, using this curve to find the value of FA, what you do is you draw the tangent here. You take the tangent and then you use this tangent instead. So let's say this is your curve fx and your tangent is tx, right? It's a straight line. So instead of finding fa, you find ta, because we know that t is always a straight line, right? So t is of this form, mx plus c. Now, if you need to find the value at 0.01, you can put it here and simply find the value without using any calculator or anything. But if you have e, let's say, and then you try to find e to the power 0.01, and you can't do it without using something, some scientific calculator or something, right? So for that reasons, we use linear approximation. And the linear so what are we making use of in linear approximation? I just discussed this thing. Instead of finding the value of this function at this point, let's say you need to find the value at this point, very close point to this. Instead of finding the value here, instead of finding this height, you're trying to find this. You're using this tangent, and then you're trying to find the value of on this tangent at this point, right? So you're ultimately making use of the equation of tangent only, right? Let's say if this is fx, then to find the first you do at approximation at, let's just do an example, then it will be more clear. Let's say you have fx equals to e to the power x only, okay? And you're taking the approximation at x equals to 0. So you're always given a point where you're finding the approximation. That point is the point where you will draw the tangent, right? To approximate things. So you'll be given this point, and then you need to find the value of e at, let's say, 0.05. Let's say you need to find the value at this point. So this is what you have to find. What you do is, first you take y minus f of 0, right? Because we're doing the linear approximation thing at 0. We're approximating it by the tangent at 0, right? So you'll do Is what I'm saying making sense to everyone? Is there a confusion or anything? If there's anything, you can tell me.
Continue.
Okay. So this is y minus f0. And here you'll have x minus 0, right? And here you have, what do you take here? The slope, right? To take the slope. And how do we just discuss it? What's the slope? Okay, if this is the tangent line at 0, let's consider this point to be 0. I know this is not the 0 point, but let's consider it to be 0, comma 0 point. Right, this point. Then this slope, this m is the slope of this line, right? Which is also the slope of this curve at point 0, right? So your curve is e to the power x. So at m should be equal to the slope of e at 0, right? Is this part clear?
Yes, sir.
So you should be, so the derivative of e to the power, how do you find the slope of e to the power x at 0? You take the derivative of e to the power x, which is e to the power x only. And then you find its value at x equals to 0. So this is e to the power 0, right? That
Ma'am,
means your
how
m should
slope
be
is
equal
e to the
to,
power x derivative into 0?
okay, I'll just write down the facts here. First is, if you have this thing, this, I know this is not the curve of e to the power
That's
x.
not into
But let's
0.
say,
It's derivative of e to the power x at 0. That is what you
yeah,
mentioned.
this is not 0. This is, I've written it as in this form, f dash 0. This is the derivative at 0. Is this what your doubt was?
Ma'am, you can explain. I guess it's from there only.
Okay. So let's say you have this point and you need to find the slope at this point, right? So the slope or you need to, what you're doing here is you're trying to use linear approximation. You need the equation of tangent, right? You're going to approximate this curve by this tangent, right? So you need the equation of this tangent. We have everything here. This is the equation of this tangent. The only problem is because this point was 0, f0. In our particular example, it's 0, f0, right? In general, it's a, fa. In our example, it's 0, f0. So in linear approximation, what you do is, the only thing that's left is this slope you don't know, right? And the slope of this curve at this point, 0, f0. And this note that this point lies on both the tangent and the curve. And the slope of both of these at point 0 is same. The slope of this tangent and the slope of this curve at this point is same, right? Is this
Yes,
bit clear?
yes, ma'am.
Okay. So you need to find that we're finding the equation of, this is the equation of the tangent. Let's just say this is your tangent Tx. We're trying to find the equation of this. So we know one point on it, 0, f0, right? So we'll do y minus f0, x minus 0. And then one more thing we need is slope. And we know that the slope of this line and the slope of this curve at 0, f0 is same. That means we just need to find the slope of this curve at 0, f0. And we already know if you've been given a function fx, and you need to find the slope of this at x equals to a. How do you do it? It's f dash a, right?
Yeah, ma'am. Okay.
That's the same thing we're doing here. So for m, it's the derivative of e to the power x, because that's your function at 0, which is e to the power 0. So this thing becomes y minus f0. f0 is e to the power 0, which is 1, right? And then, should I write it? It's e to the power 0. Then you have this thing also e to the power 0, slope, and then x minus 0. So this becomes y minus 1, x. So this will be y is equals to x plus 1. So this is the equation of the tangent that you're going to use for linear approximation. Now you need to find the value of e to the power 0.05, right? So what we're doing, what we said here was, why are we using this linear approximation? Because we don't know how to find this number. It's very complicated. So instead of using this curve, instead of finding the value of this curve at 0, 0. We're trying to find this tangent's value at 0, 0, because if this was the point where you drew the tangent here, then for very close points to this one, so if you have a point very close to this, then the value of this function at 0 and this line at 0 is going to be approximately same, right? Because they're very close. If this is your curve, let me draw it here. If this is your curve, and if you do this thing here, it touches and passes, right? So for this, if this was the point, then this lines, I'm not able to make it properly here, but that's what happens when you have something like this and this line passes through here. Then for the point here, this value, this function's
Points
value
that are
and
very
value
close
here,
to that
yeah, they're very
tangent
close.
will
So it,
you can approximate it.
yeah, because the points are very close to each other. That's why the tangents, the value at this curve and the value at the tangent here. Let me just, do we have a, oh, we don't have an image of this. Otherwise, I would have explained it there. So at this point, if you have this, and this is the tangent at this point, say, then at this point, the value is almost going to be same. So no matter if you take it on this curve or on the tangent, they're very close to each other. That's why it doesn't matter. You can approximate it using the tangent. So instead of finding e to the power 0.05, use this curve, because it approximates e to the power x, right? The linear approximation of e to the power x at x equals to 0 is this. That means for points very close to 0, you can use this thing instead of using this. So instead of doing this thing, you can just simply do y is equals to 0.05 plus 1. Or if you have to find, let's say, 0.00001. So instead of finding the value of e to the power x at 0.0001, you can just use this curve. Is that okay?
Yes, ma'am.
Okay. So I think we've covered everything in this week. If there's any doubt, then we can discuss that. Otherwise, we can end the session.
Ma'am, one doubt that I was asking,
Yeah.
that practice assignment 8, question number 5, option 2.
Ma'am, just I want to take the screenshot of the last thing that you have explained for the revision thing.
Just 1 second. Practice assignment 8. Which question?
Question number 5, option number 2.
Question 5, option 2.
Yes, ma'am. Question number 5, that second option, the thing that I
Yeah,
asked you.
yeah, that's what I explained there. No, what happened?
Yes,
Take very
that 0
particular
by
case
0
here.
form. Yes.
It's this one, right? So if you have this thing, we said that you can separate the limits over these two if the limits
Yes.
are not of the form 0 by 0 or infinity by infinity. If you're getting this form, then don't do. That means you're not getting the limit, right? What's the purpose of separating the limits over these two functions? It's to find the limit of this entire function. But if you're getting 0 by 0 form, that means you can't separate it over these two.
Yes,
You're not
ma'am.
getting a number. That's why it should be false.
Yeah.
Is that
Yes,
okay?
ma'am. Yes, ma'am.
Okay.
That was the doubt. Yes, ma'am. Thank you. Clear, ma'am. Yes.
Okay.
Ma'am, if I can highlight one thing.
Yep.
We want the live recording session of the previous, because for the previous one session, for the week 5 or 6 summary, I have the material. But the thing is that the voice lecture, like the total video thing, is missing. So if you can
Are you
guide us.
talking about the TA sessions?
No, the instructor session specifically. TA session is fine, but I want all the live recordings and the material, like the PPT lecture, whatever we have discussed, this blackboard. So where we can find it?
You're talking about the notes, right?
Yeah, notes and the total material.
We just have notes and live lectures uploaded on the YouTube channel.
Okay. Does the channel have the same kind of format where we have explaining and all the things?
It's this session only. This session is recorded and it's put there.
Okay.
Ma'am, I just wanted to take the screenshot of the last thing that you have explained, the tangent one. If you can zoom in a little bit. A little
Just
down.
before the previous quiz 1,
Yeah.
in the like they have uploaded the let me check the supplementary content. Live session slides named as live session slides. So where I can find the live session slides for week 6, 7, 8, those.
They must not. You have a drive or something. It must be uploaded on your portal.
Okay.
Ma'am, there is one doubt. When you were explaining the limits, if you can go a little up, when you were explaining the limit of that mod x, the mod x example, when I asked you, you were
This one.
yeah, ma'am. Yeah, the right hand derivative, I can understand it's mod of h minus 0 upon h, but the left hand derivative, I don't get it. Like why we are doing it mod h minus 0 upon h, because it should be 0 minus mod h upon minus h kind of. I don't know.
Okay.
A little bit,
See,
I'm having a little
there
bit
are not
doubt because
two
whenever we are
ways.
doing left hand derivative, it's
I do it this way, but you can do it that way too. So if you have mod x and you need to find the derivative at x equals to 0, you're suggesting that you should be taking 0 minus h. How do we do it? We take f of a plus a minus h, right? So it's f of, I was not using this thing, f of a by minus h, right? Where your h tends to 0 plus.
no, ma'am,
Because
I'm saying
how do
f
we know
a
this?
minus f a minus h, na, it should be because
It's
f
a
a is
minus
greater.
h only.
No, ma'am, f a minus f a minus h because f a is greater here. F a is greater,
Yeah,
so
okay. No, it's that only. What's written there? It's fa minus h only. It doesn't matter which one's written. In the definition also it's written, no?
I think I'll.
Yeah. It's fa minus h minus fa. It's this only. That's how you find the left-hand derivative. Now, I haven't used this form. I've used this instead. If you use this one, you'll get the same answer. But because it's already explicitly mentioned that you have to take h greater than 0, that means in this one, the h tends to 0 plus 0 from the right side, right? So if you do this thing, you'll have 0 minus h minus 0 here and then minus h here. And because you know that your h is positive, so this you're going to get as your h is positive, so minus h is negative, so it's going to be minus of minus h. So you'll get h here and a minus h here. This will be minus 1. So getting the same thing. From here also you get minus 1. If you will use fa plus h minus fa by h as h tends to 0 minus, then also you'll get the same thing. These are one and the same things. Is that okay?
Just see, ma'am. I'll see more examples and I'll come back to you maybe in the next class.
Okay.
Ma'am, can we have the link for the handwritten notes of like this part?
What?
Can we have today's class that you have all written like the link of these notes?
Yeah, these notes are uploaded, no? You're going to
No,
get
ma'am, like
this.
your handwritten notes, like all this part that you have written.
Yeah, okay. I'll upload it.
Yeah. Thank you, ma'am.
Okay. So there's nothing else, then we can end the session. Yeah. Okay. Bye, guys.
Thank you, ma'am.